Okay.
Okay. So today we have our speaker, Dr. David Isele. David and I used to be in the same research group. He obtained his MS degree in robotics and PhD degree in computer science from the University of Pennsylvania. And currently he's a senior research scientist at the Honda Research Institute. And his focus during his PhD and currently is on using machine learning and artificial intelligence in robotics and autonomous agents, and more specifically in the domain of self-driving cars. Today, we are going to have his talk on interactive decision-making for autonomous vehicles in congested traffic. And during the talk, if you have any questions, you can, as usual, type in question and answer. And I'll try to raise questions during the talk. And at the end, we will also have some time for questions if you come up with your questions after the talk. Thank you. And with that being said, I leave the stage to David.
All right, thank you, Mohammed. Let's share my screen. Seems to, this one, share. All right, you guys can see my screen now? Is there a yes?
Yes.
Yes.
Okay.
Yes.
Yes, I was muted.
All right. All right. Hello, everybody. I'm David Isele. Thank you, Mohammed, for that introduction. And why are my slides not moving? Okay. So as Mohammed had mentioned, I work for the Honda Research Institute. The Honda Research Institute is a subdivision of Honda R&D, and we have three different branches: the Europe branch, the Japan branch, and the US branch. The Southern Equator isn't really well represented here. And the US branch includes a Silicon Valley and a Detroit office, and I'm at the Silicon Valley office. I wanted to talk to you guys a bit about the type of research that we do at Honda Research Institute. So let's get these videos started. Okay, so we have work in crowd navigation. So here we have a ball bot, which has been made by Honda. And this is research looking at being able to navigate through a crowd, go to a location with lots of people walking into your way and walking around you, while avoiding collisions and moving safely and smoothly. We also do a lot of work into human factors, things such as situation awareness, driver attention, driver focus, and ways to address issues if a driver is not paying attention, and things we can do to increase safety of driving. There's a lot of computer vision and scene understanding work going on. We usually focus on driving scenarios, so we'll look at segmentation and scene classification, such as shown here. We also have a lot of publicly available data sets that people can use for these sorts of problems. Moving towards more pure robotics, we have work in manipulation. So here we're looking at manipulating deformable objects. We're also doing a lot of work here in terms of regrasping and changing grasps when you're holding an object. Moving somewhat closer to my line of work, we have work in behavior prediction and looking at how humans and other agents move through space and predicting their behavior. We also have a material science group that is doing lots of work in nanofabrication and working with nanomaterials and how to grow crystals and things like that. And one application that's been emerging from that is related to battery technologies. So we've actually have several patents related to flexible batteries. And here is a example where they take the battery out of, I guess this is an Apple Watch. And it's actually this duct taped strap over here that is powering the watch. And that's a completely flexible battery. And then we also have work mostly going on at the Detroit office on V2X communication, so vehicle to vehicle, vehicle to intersection, things like that, trying to increase the safety of traffic driving. And that's just a sample of some of the research going on at HRI. Now, a bit more about what HRI is. So we're, as part of a research and development company, we're the research branch of that, specifically the most forward-looking research part of that. We're entirely funded by the parent company, so we don't have to go around looking for grants to fund our work. And we're potentially more coupled to real products. I say potentially because when I was a grad student, there were several people who started startups immediately out of grad school, and that's probably the case with you guys. And also, we do have some more forward-looking, purely scientific research, as some of the material science stuff is. We're also allowed and encouraged to publish and attend conferences. And so if you like doing research but aren't interested in staying in academia for whatever reason, this is perhaps something you should consider. And I say this because we're hiring. So if you go to our website, as I show here, there's a careers tab where we have associate contractor and intern positions open. I will say that if you are interested in an internship, currently the posted positions are for the spring. So if you want a summer internship, check back in a couple weeks. All right, so now that my commercial is over, let's get started with the actual research. So we're talking about interactive decision-making for autonomous vehicles. And so the problem statement is, say that we are in congested traffic and we're trying to merge to get around this obstacle or this ambulance. Most solutions look at something where we're going to just wait for a gap to appear and then move into that gap like this. But in dense traffic, it might take a very long time for a safe enough opening for a car to merge into. So we'll just be waiting and waiting, and cars will come up behind us and get frustrated and they'll honk at us. And so this is something that we want to avoid. And to do this, we need to be able to negotiate with other traffic participants. Realize that we have to initiate a behavior to create an opening. So position ourselves in a particular way that indicates that we want to merge in. And then we have to observe the response of the other agent, because they might not necessarily let us in, they might. And we need to be able to interpret their response and then continue to act accordingly and interact to accomplish the maneuver. So as an example of the types of behaviors we're looking at, here is a human driver shown in the red car. And this was a target video that was collected as something that we wanted to see if we could actually replicate on an autonomous vehicle. All right, so the first approach I'm going to go through kind of gives an overview of the structure of a common approach that we've been using, and then I'll branch off to look at how we can improve this approach later in the talk. But we're going to be looking at game trees. So a simple example of this is at tic-tac-toe, where you consider all the first moves. So there are 9 first moves, but due to symmetry, you can reduce it to just 3. And then based on whatever first move was taken, you can branch that into the next options that are available. And in a small game like tic-tac-toe, you can actually do this all the way down to find the winning games. You can and then you can back propagate up to select the best action. There is, however, as you can see, an exponential branching factor. So for even slightly more complicated games, these things become infeasible in the brute force strategy, and more efficient mechanisms need to be incorporated. However, there is quite a lot of work into doing that, and these strategies are already used in chess and Go and other sorts of artificial intelligence systems, as I'm sure you're aware. And one thing to mention here is that these are strictly more powerful than your typical MDP reinforcement learning problems, as they allow for non-stationary agents or agents that change their strategy over time or learn over time. So you're not just training against an environment, but another agent who also might be learning and adapting along with you. And when we want to look at converting these tools to autonomous driving, we have to take into account some concerns like adapting the continuous control to a discrete time and discrete action space. Also, we need to look at reducing the computation costs so these things can run in real time. Basically at frame rate, we usually have a slightly lower standard where we try to target about 10 hertz, but anything that takes longer than 10 hertz to run is effectively useless to us. And we also have to have prediction models where we're able to understand how our adversary or other agents in the scene are going to behave in order to be able to propagate down these trees. So to work through an example of what this looks like in autonomous driving, so we're going to start with the traffic participant shown in blue, and we're just going to consider interacting with one of these other agents to make it a simpler problem. And here, that agent has two different choices. They can either yield for us or they can continue driving, and that is represented by the two branches here. And then our vehicle will also have a set of actions. For the simplicity of visualization, I'm only going to show two, but we do have much more in practice. And then if these actions on the tree are shown one after another, but they're happening simultaneously in practice. And if you just consider one stage of this, you get a matrix game. And then what we're going to do, so in this case, we have two actions, and what looks like the better action is to merge more to the left here. But if we look at the case where the car continues, it puts us in a hazard condition. And so we're actually going to err on the side of caution, say that this is an unsafe action to take, and prune that from our tree. And then we're going to continue down the tree and select the action with the best reward. And then back propagate that up. So when I talk about selecting the action with the best reward, this is for autonomous driving, there are actually multiple rewards that we might want to target. So we might have something to accomplish our goal, saying that we continue moving forward and make forward progress to reach our goal. We also want to do this safely, so minimizing risk, avoiding collisions entirely. We'll also probably have rewards in there to make sure that our behaviors are smooth, so that we're easy to understand to other traffic participants and we don't make any riders sick. And so when we have multiple objectives, we don't really have one fixed solution. We have a Pareto frontier, and the best solution is anything along the frontier. But in practice, we want to have one single reward that we can pick. And so there's heuristic approaches to do this, such as using the L1 max. So I'm showing a example sampling strategy here on the left, where every rectangle in perspective is a different goal position. The grayed out ones are hazard cases. So all the colored ones are valid solutions, and the thickest one is the one that actually is being chosen at this point in time. And here is a visualization of what the reward space might look like. Okay, but an issue if you're going to be running these things on a computer, in order to interact with an intelligent agent, you need an intelligent agent to interact with. So kind of a chicken and an egg problem here, where if we want to have a simulation where we're interacting with intelligent agents and we have an intelligent agent in the system, well, we could just take whatever the system is using, put that on our agent and then use that. We have an intelligent agent. So in practice, what we do here is that we're going to use a bunch of heuristics that are generally going to be specific to a particular behavior, and use that to produce something that is human-ish for the other traffic participants. These do tend to be very specialized to a particular situation, and you can just think of them as a bunch of if statements to give us different behaviors. And we're going to make them stochastic so that we can have a larger variety of behaviors so that we're not always responding to one fixed specific agent behavior. So the way that we're doing this in the merge case is that we have two randomized thresholds. So the shaded regions here are depicting a uniform distribution where we're going to sample a yellow threshold from the distribution and the black threshold. The yellow threshold is going to correspond to being noticed, and the black threshold is going to correspond to the car yielding. And if the car notices us and isn't yielding, they're actually going to be accelerating to block us. So that's what's happening in the first case. We haven't crossed the yield threshold, but we have crossed the notice threshold. So they're accelerating to block us from merging into that gap. Here, we haven't crossed the notice or the yield threshold. So the car is just driving usually. They don't see us at all, and just continuing normally. In this case, we've crossed the yield threshold, so the car is actually going to back off and yield for us to let us in. And one of the nice things that comes from this particular design where we have two thresholds that can cross each other is we can have a case where we first cross the notice threshold and the car accelerates to block us, but then we are persistent and cross the yield threshold, and then the car backs off and lets us in. And I want to mention that this is intentionally not the way that we're modeling the vehicles for our autonomous agent. So we want to have, because if we were to perfectly match the model that we're using for our autonomous agent that's doing the learning to the behaviors that are being generated in simulation, we're kind of setting ourselves up to succeed, but it's not a realistic situation. So we do want these to be mismatched to make sure that whatever model we're putting on our vehicle generalizes to cases that are beyond the specific model itself, since humans aren't going to follow a specific model. And why is my slide not progressing? Okay. And so this is what it looks like playing out in simulations. So the autonomous agent is the orange one here. And you can see that we try to merge. The cars are blocking us, not letting us in. This one lets us in, and we go ahead. And so this is what it looks like in simulation. One of my advisors liked to say that simulations are doomed to succeed, in that all they're doing is representing all the knowledge you currently have about the system, which means all the stuff you don't know, which is what's most likely to trip you up, is not going to be included in the simulation. And it's very frequently the case that I'll be reviewing papers and looking at approaches. And when you actually try to run them, even in a slightly different simulation environment, they won't work well, because there's a lot of things in terms of perception errors, controller delays, localization errors that very quickly confound things that require very strict adherence to the particular rules they have set up. This framework, however, has been translated to a real vehicle. So here we have the autonomous vehicle shown in red, the red Accord, and we're trying to merge into the gap in front of this black minivan. And so there, the black minivan lets off and we merge into the opening. And here we have a similar setup. Again, we're going to be trying to merge in front of the black minivan, but here the black minivan's not going to let us in, so we're going to persist a bit, keep trying to get in, and then we're going to back off, and now there's an opening behind it, so we're going to merge behind that. Shall I take the question? Can you read that to me? All right. I will keep going since I don't hear anybody. All right, so this is an overall framework that we're going to kind of be considering for behavior. But there's a lot of, oh, go
Sorry,
ahead.
I can read the question for you.
Yeah.
I was trying to read it to reword it, but I think I just read it. So it says, since that edge cases are usually the most interesting ones, but they occur less frequently in the real world, how are those simulated and how is knowledge about them incorporated into models?
Yeah, so there are tons of edge cases. It actually creates a issue when training systems, because there's huge mismatches in data, for which causes problems for a lot of machine learning algorithms. I mean, even simple cases, things you wouldn't think of as necessarily being edge cases, such as lane changes. When you're looking at highway data, almost all highway data is going to be cars driving straight along the highway, which turns something that we think of as being pretty common as a lane change into something that, from a machine learning point of view, is more likely to be considered an outlier. And then you, of course, have much more strange cases like cars, like their tire pops or something like that, which are, again, frequent enough occurrences when you, especially when you take them all together, but in terms of the data are very infrequent. And the way to approach that, to actually answer the question, is that we try to come up with a model that is very robust and works against a lot of different cases. And then it's kind of a probability game. If you push it and kind of slowly over time build up confidence that it can handle things that you haven't seen before, when you start to see it handle things that the system hasn't seen before. That doesn't mean it handles everything. And getting guarantees that you can actually handle everything, I don't think is even possible, because driving is not a adversarial setting. And however, you could do something like take an agent and have them be adversarial, like a car on the road who wants to hit you. And that would basically make driving impossible, because if you imagine driving and somebody's trying to hit you, they're probably going to succeed. So guaranteeing it in all cases is not, I don't think, at all feasible, but we try to test it in a large enough suite of ways. And that's something that's important for simulation, is that there's a lot of noise on the system related to control noise, control delays, perception noise, perception errors, localization noise. A lot of these noises are also not Gaussian. So they have to be designed in ways that actually match the sensor inputs that you're getting. And incorporating that noise into the system when you're training and when you're testing gives you a sense of just how bad you can make things and have your system still be robust to it. And also lets you know how the system is going to fail. Is it going to start braking a lot and start driving very slowly and cautiously, or is it going to start having collisions? And those are things that you can get at by closely investigating the noise and the failure points that you expect to encounter. All right. So places to improve. The action generation that I had mentioned in the first section related to a sampling strategy. This actually worked quite well at low speeds, where the behaviors were smooth. It was able to indicate nice actions. It was somewhat specialized to the lane change scenario, the way that we were doing the sampling. And it also didn't generalize well to high speed. So there's, in terms of producing smooth actions that are more general, that's one way to improve this. There's agent modeling. So there's the first method I showed, we have this very limited case where the other traffic participants yield or don't yield. Of course, there's a lot more complexity in terms of what a traffic participant is capable of that we want to be able to incorporate into our system. And then we also want to be able to increase the number of agents that we're able to consider and incorporate into our models so that we can handle the entire scene and not just one targeted agent. For the purposes of this talk, I'm going to be focusing on just the later two, as I believe this is a artificial intelligence community, and I think those ones are the topics that are a bit more relevant to you guys. All right, so for modeling. So here are some, one more to get that one going, okay. So here are some models that are used. So first, constant velocity. This is kind of the simplest baseline. It's actually a very good baseline, as came up before in the, when I was talking about outliers. When you're just following along on a highway, a straight constant velocity prediction is going to be very accurate, especially if you're only going to look at maybe the first 3 or 4 seconds. When you start getting longer times, you start having errors. Here you can see that because the road curves slightly, you start going off the road. But I do want to point out that this is a very strong, very reliable baseline, because there is a lot of, I guess, trying to remind people of this in the literature. There's several papers. A recent one from Scholler et al. Is going through and taking a lot of the developments in prediction, comparing them against constant velocity and showing that they don't perform as well. So always compare against some simple heuristic baselines in addition to this most similar machine learning algorithm. And you can actually get constant velocity to behave even better if you start incorporating road priors, such as locking it to the lane and having the constant velocity move along that given lane. We can improve upon this constant velocity using what's called an intelligent driver model. This is a model that was designed for car following or lane keeping, where it determines what your speed should be based on the distance to the car in front of you, as well as the velocity you're currently traveling at and the velocity that car in front of you is traveling at. And because that's a parameterized model, Hoerman et al. Did work into looking at parameter estimation for that model, applying it to other traffic participants. And this allows us to treat the different drivers on the road as individuals, so we don't have a fixed model for everybody. And this improves upon the constant velocity model in that it models braking. However, it can't change lanes, so there's still a lot of restrictions in this case when we're just learning the parameters of the IDM model. For a more unrestricted model, you can have something such as inverse optimal control. This is less constrained, and so you can get behaviors such as lane changing in theory, but training these models requires more data. Now, and so you can see this is actually where we have learned a lane change behavior, where we see that the modeled agent in green is actually doing a lane change before the human expert and driving a bit more aggressively, which is nice. The reason that I say in theory is that when you look at these inverse optimal control and the less constrained behaviors, you'll also see a lot of things like this, where it just feels comfortable moving through another agent and traveling down across multiple lanes. And this is, of course, not any behavior that you would want to have on a real vehicle, and not a good model for other traffic participants either. And so when you have these more complicated models, you can cherry pick examples that look very nice, but you also, in terms of robustness, they don't hold up as well in practice. And so reducing the constraints makes, I think I have this backwards, reducing the constraints makes learning easier, but it makes, but you get more undesirable behavior as you reduce the number of constraints. Sorry, no. Wait, I do have that right. Reducing the constraints makes learning harder, and it makes undesirable behaviors more likely. And so next we're going to talk about how to balance the expressiveness with the ease of learning. And specifically, a model that we have found that works quite well is level K reasoning. So here's a scene from Princess Bride, which is a movie, if any of you have seen it. And I think it kind of depicts the level K reasoning quite well. So the character in black has posed a challenge to the other character, where he has placed 2 bottles in front of them and has said that he has put poison into one of the glasses. And it's a intellectual challenge where the character in the front of the screen has to determine which glass to drink. And a level 0 agent would just drink the glass that's in front of him, as that's the default. A level 1 agent would say, you would poison the glass in front of me, so I would drink the glass in front of you. A level 2 agent would say, you would know that I would think that and poison your own glass, so I should drink the glass that's in front of me. And you can continue going deeper and deeper into this reasoning level. In practice, humans tend to reason at either level 1 or level 2. There's an asterisk here because it, of course, varies by circumstance, and humans are also often not rational. But there are settings where we observe that humans behave in this level K reasoning fashion, where some humans will be level 1 and some will be level 2. Some will also be level 3. Often in the literature, this is sometimes called 1.5. And we've actually done work where we look at doing this on robotic systems, and we also see diminishing returns in autonomous driving after level 2. So it suggests that there's reason for us to stop at level 1 or level 2 as well. And so a restriction of level K reasoning, which you might have noticed, is that the assumption is that the other agents will behave like you. And if you're behaving rationally, that assumes that the other agents will also behave rationally. And that's a bit of a restriction because we want to allow agents to behave differently from ourselves. We also want to account for agents who might behave irrationally. And so there's an extension to the level K iterative reasoning model, which is quantal level K, which incorporates probabilities to account for some non-optimal decision making. So you can think of this as a softmax, where we will expect the agent to take the most optimal action with a higher probability. And so here we have 2 parameters. We have the reasoning level, which is the depth of reasoning that the agent goes to, as well as a rationality coefficient, which is going to describe how much the agent adheres or deviates from the optimal action. And these 2 parameters are describing a 2-dimensional latent cognitive space, which we can then learn to model online to interpret the behavior of the other traffic participants. Now this policy then gets incorporated into a POM-DP, which is solved using Monte Carlo belief tree search in the case of this paper. And we're also designing our reward for active exploration so that we take actions that help us infer the latent cognitive space so we can quickly learn the model of the other traffic participants. And so here you can see the results of this. On our planner, we have our autonomous agent is shown in orange. We indicate that we want to merge. Here the white car yields for us, and we quickly accomplish the merge behavior. Where in the second case with the red car, we again indicate that we want to merge, but the red car doesn't let us in, so we have to go in behind it. And because we have this active exploration going on, we're able to more quickly infer how the other traffic participant is going to behave, allowing us to act more quickly than related work from Lee et al. Is the case that we're comparing against here. Okay, and so next I'm going to talk about how K-level reasoning is in more general interactions, how it extends beyond a a two-player game and how it also extends to cases beyond autonomous driving. So here we're looking at recursive reasoning in deep reinforcement learning. So now we have a full learning pipeline. And here we're going to train the individual agents in isolation to increase their exploration. And then using those individual policies, we then have a central actor who is going to perform message passing and iterative reasoning. And the message passing and iterative reasoning, which we're incorporating, allows us to determine the actions that are going to be taken by the other agents. And then once we have the central actors, we can then train the critics to match the reward and the value that we observe from our interactions. And this has some nice benefits when we look at comparing it to other work in the literature. Because we have this iterative reasoning process, we see that we pick up some benefits. So here are two different toy problems we're looking at. The first is a zero-sum case. So the first agent is going to get the max reward whenever both of the actions are the same. So if both agents play -1 as their action or +1 as their action, then we get the maximum reward. And then the inverse is going to be true for the second agent. Whenever the actions are different, they get the max reward. And so in practice, you can imagine this being a cyclical behavior. So as agent 1 learns a policy that plays -1, then agent 2 is going to switch to a policy that plays +1 to put us over here. And then we're going to switch our policy to, or agent 1's going to switch its policy to play a +1 and move us over here, and we're going to get this cyclical behavior. And that's exactly what we see from algorithms like PPO and COMA and multi-agent soft actor critic, is that we'll have these oscillatory policies. However, from the iterative reasoning, we're actually able to target in on a mixed policy, which is an optimal policy of keeping us in the middle here. And the second toy problem that we look at is, this one is a cooperative game, but we have a local optima and a global optima. And because the local optima is larger, it is possible to more likely to draw you into the local optima and get you stuck there. And that's exactly what we observe, is that many of the algorithms get stuck in the local optima, whereas R2G, which is our algorithm, is able to escape the local optima and find the global optima. And these are just toy problems, which are encouraging, but limited in what they show. So here we have a 3-agent cooperative game. So these are particle world environments. Here the target is to have the 3 different agents cover all of the 3 different goals. And so if 2 of them go to the same, then it leaves 1 uncovered and they get less reward. And here we can just directly compare the total reward received, and we see that our algorithm has the best reward on average. In cases that are in competitive games, it becomes a bit more difficult to analyze because you have your agent and you have your adversary, and if you're training both of them, if you're getting more reward, are you getting more reward because your agent is better or because your adversary is worse? And you of course don't want to say that you have a better algorithm because you have a crappy adversary. And so one way, I guess, immediate thing that might occur to you is to then use the adversary from a different algorithm. But then you have biases where if an algorithm was trained against that agent or that adversary versus not trained against that adversary, you would have an advantage going to one. So we're looking at all those differences where we're taking our algorithm and looking at how we do against the other agents policy. So we're actually at a disadvantage in these cases because the other agent has trained against that adversary, and we're showing how well we can do against that adversary. And so yeah, because there's these trading offs, there's a lot more plots to compare, but you can see that red is usually good, doesn't always win. I think there's some failures over here. Yeah, like this guy, we don't do as well. But yeah, we're seeing that. And then we also look at it in this robot sumo example where we're trying to learn the behaviors of these simulated insects, and the goal is to push the other agent out of the ring. And again, you see that we're doing the comparison where we play at a disadvantage, looking at how we do against the agent we didn't train against, and still you see that we often have better bars or better results. Right, time.
Quick question.
Sure.
So what would in this model induce a driver to slow down to let an incoming car go in? What would be his benefit?
So as I started off the talk with we have a case where the conservative agents or the safer agents are, the more likely they are to just wait, and waiting is causes problems. It backs up traffic and causes traffic delays. So I think the goal is to have is to figure out how we can design very efficient agents that are still very safe. Now we might not want, and so there's a desire to have a very aggressive agent, or at least to be able to create a very aggressive agent so that we can move as quickly as possible and still maintain safety. In practice, when we deploy these things, we're probably not going to want that fully aggressive agent, and we're probably going to want to be able to adjust how aggressive the agent behaves so that we don't have a rude traffic participant. But being able to act swiftly and safely is kind of a target that we have, that we can act very intelligently and very precisely. Yeah, I think that hopefully that answers the question. All right, so now I'm going to talk a bit about increasing the number of agents. So this overall pipeline is doing a lot of other things in terms of we're restricting the learning here to only be about the prediction side of things. And so we're not doing full end-to-end learning, but we're using model predictive control to govern the behaviors. So the way this pipeline works in a kind of crude overview is that we're going to pre-compute trajectories for all of our different driving intentions, evaluate the safety and cost with the predicted positions, and then choose a candidate that meets the safety constraints with the minimum cost. But this middle block here where we're evaluating the safety and cost is going to be done by a neural network. Specifically, we're using social SGANs or social GANs. So this is a variant of general adversarial network designed for interaction with traffic. Well, I guess it was originally with pedestrians, but with crowd navigation. But one of the nice benefits of using a neural network in this case is that it's going to produce the predictions for all the other traffic participants simultaneously. So that removes the combinatoric explosion that we get from trying to consider all the different agents' individual actions. Whereas now we just have how the entire scene will evolve. And additionally, because we can pass our inputs in batch, we can handle multiple inputs at once. And so we kind of get two different aspects of speed increases when we use neural networks, because we just have to do a forward propagation to get out our predictions. So what this looks like in practice is, so here we have our ego agent shown in the middle in orange, and then the other traffic participants are shown in gray. The blue dots indicate the past history. The yellow dot or teal dot here show the current position. And this is at time equals 0. So then at time 1, we get the prediction from the social GAN of how the other traffic participants are going to evolve. And then based on that, we can input our action and then get the next step of how the traffic agents are going to evolve, et cetera. And we can pass in our actions in batch to get this for multiple different intentions and then select the best intention. And here, the reason that there are circles that are outlining the vehicles is that we're able to compute the distance between two circles in a closed form manner, which allows us to more effectively construct the quadratic program. I've been told that if you don't have slides with math on them, people think what you're doing is too easy. But specifically, I want to draw attention to the line here, which is the collision avoidance line. And this is what is being carried out by the social GAN, or the learning pipeline. And the rest of this is being handled by a quadratic program solver. All right, and I think that's the end of my talk. And I'll play these videos while more questions build up. So here we have the human driver. This is taking the same ideas and applying it to a T intersection. And so your view is a bit restricted because we only have forward-looking cameras showing things, but that's what a human driver looks like. And then here we have an autonomous vehicle accomplishing a similar maneuver. Here we're waiting for an oncoming traffic car to drive past, and then now we're moving forward. All right. So there's a question.
Yes. So it says, is Psi an important branch of research at HRI? If so, could you talk a bit about challenges in understanding AI models, decisions for autonomous driving?
Sorry, well, is what a important?
Explainable AI, sorry.
Oh, explainability, yes. So we do have a group that is looking specifically into explainability, also how that goes along with trust. So not just are we looking at explainability in AI, but also how those explanations impact whether or not a person trusts the specific system. So yes, that is something we're looking at. For our group, we have, I guess, looser restrictions on what we consider explainable, where we want to have visualizations so we know how the other traffic participants are going to act. We know what we're predicting they're going to do, and we can observe if they actually do that or they do something different. That's not as tight as the more formal definitions of what are considered explainable. But so definitely yes, we need to have some idea of what our system is doing at all times. And then yes, but I'm not the one doing it in terms of the actual field of explainable AI.
Thanks. So I have a question myself. So deep RL is known to be quite slow, and you need a relatively large amount of data to train them. So I wanted to know, is that a challenge for you, or since you can generate synthetic data, you can just use synthetic data and it's gonna give you decent performance in practice?
So how do I put it? So my work is mostly with interaction, and currently we don't have that's difficult to do with only data sets, because when you have recorded data, you can see how other agents interact, but you don't have the counterfactual of if you were to remove that agent and do something different, the scene still plays out the same way because it's recorded. So we tend to work in simulation. However, other groups at HRI are looking at where they're looking at prediction, and they're looking at classification problems and other computer vision problems, are very much in the opinion that more data equals better system, and have put a lot of effort into collecting massive databases specifically for that purpose. And those, as I mentioned at the beginning of the talk, some of those data sets are publicly available. So other researchers are welcome and encouraged to use them. So yes, more data does help with deep learning models. How well that allows the system to generalize is kind of a case-specific issue. For things like object identification, I guess ever since YOLO, like object identification works very, very, very well, and is quite reliable for more complicated tasks. We're not there for all of them, but that might, whether more data will get us there, or whether we need to come up with more clever algorithms, or maybe both. That's something that's to be seen.
Okay, thank you. Any more questions? Okay, thank you so much for your presentation. And I guess if there's no question, we can end this session, and then you can probably, I guess you have a break, and then you're going to meet with